welcome back. So this is lecture 29 in this course on Bayesian modeling. The topic of today's lecture is importance sampling. So where we left off in the previous lecture was we were discussing grid approximation approach, and we saw 3 steps: proposal generation, evaluating the proposal, and then accepting or rejecting the proposals as valid samples on the posterior. Okay. So those 3 steps we discussed for grid approximation. Okay. So let us take it off from where we left. So what if in the grid approximation approach, rather than having one parameter, you have 2 parameters to estimate? And that can happen, for example, in case of let's say you assume that data point, ith data in your experiment comes from a normal distribution with parameters mu and sigma, mean and standard deviation. And then you set up some prior on mu. Let's say prior on mu is P of mu, prior on sigma is P of sigma. Okay. So in this case, you will need to estimate posterior distribution of P, mu as well as posterior distribution of sigma. Okay. So what is the problem if you do it through grid approximation? Well, if you want to do it through grid approximation, you will need to do 2 things right. So one is this, that you need to divide the grid for parameter mu. Okay. So in a reasonable range, right? So let's say I know, let's say this is a reaction time experiment. So I think that mu could be between, let's say, somewhere around, so I want to take a reasonable range. So it won't be negative at least. So let's say between 0 and 2000, right? Can't be more than that, right? So let's say I take this range between 0 and 2000. And for sigma, let's say I took a range between, so sigma can also be not negative. So it could be anywhere between, let's say, 0 and 200. Okay. Now, what I will do, I will generate this 2-dimensional grid. This is what you will have to do for grid approximation approach. I will generate this 2-dimensional grid where each grid will be a set of parameters. Each grid will be a proposal. Okay. So see, I'm basically dividing this parameter space of mu and sigma into equidistant points, right? So these are equidistant points for mu, these are equidistant points of sigma, right? But when I take their combination, I end up with this 2-dimensional grid. So this particular parameter value pair, so this is, you can call it, let's say this one you can call mu1 sigma1. So this is first proposal. Similarly, this one is mu2 sigma 1. This is the second proposal. So you are proposing pairs of values of mu and sigma, right? So basically pairs are generated by these equidistant points on parameter space of mu and sigma. Okay. So this is how you are generating proposals. So basically you are generating samples of mu star and sigma star, and you are combining them. You are checking all these pairs, right? So this is the grid, and each grid is our proposal here. Okay. So each of these, so for example, this is a proposal, this is a proposal, like that. And these are basically pairs of values of mu and sigma. Okay. Now, when we evaluate the posterior, so what can happen is that, let's say the posterior of mu, parameter mu, is somewhere here, let's say between 200 and 300, and the true posterior of sigma is, let's say, between, let's say, 10 and 50. Okay. It's usually not that less, so let's say 30 and 50. Okay. So let's say this is true posterior of mu, this is true posterior of sigma. Okay. So if that is the case, which space in this grid will have non-zero posterior density? So this is the grid panel. So which area in this grid will have non-zero posterior density? So it would be the space which corresponds to mu values between 200 and 300 and sigma values between 30 and 50. So let's say that space is here. So let's say this is the mu value 100, this is 300, and sigma between 30 and 50 is here. Okay. So this will be basically just this region. So this is the region that would have non-zero posterior density. All other grids, all other proposals would have close to 0 or 0 posterior density. What it implies is this, that when you are generating all these proposals, okay, you are suggesting all these proposals, and this would be basically, let's say you are suggesting 10,000 grid points for sigma and 10,000 grid points for mu. You are proposing these many number of samples. So this is the number of proposals you are generating, and out of this only, let's say 10,000 proposals have non-zero posterior density, and most of them have 0 posterior density. So basically you are wasting a huge number of samples, okay, because the posterior density is only in this region. The rest of the proposals you are just throwing away. You need to reject them because they have 0 posterior density, okay, and that's a huge wastage. And this wastage is going to increase as you increase the number of parameters. Okay, so this is a waste of computational efficiency, because computationally it becomes more and more expensive as you generate these many proposals, right? So as the number of parameters will increase, the number of proposals you are going to waste are also going to increase, right? So right now it was 10,000. If you have 2 parameters, it will be 10,000 to 10,000. If you have 3 parameters, these many proposals will generate, and only a very small fraction of them will have non-zero posterior density. So this is a huge wastage, right? So what happens because of this is this empirical result, that as the number of parameters increases, your rejection rate increases exponentially. Okay, so what it implies, that computational inefficiency or the computational cost of applying this grid approximation approach will increase exponentially as number of parameters will increase. So what it means is that this approach cannot work when you have 2 or more parameters. Okay, so this approach can work only for very simple model. Okay, and the reason why this approach cannot work is precisely because of how you are generating proposals. So there is, the main problem lies in proposal generation. Why the problem lies in proposal generation? Because you are generating too many proposals which have 0 posterior density. So although the actual posterior distribution lies here, but you are still generating all these proposals here in this region and this region. Okay, and in fact in reality the actual true posterior lies in a very small range, let's say somewhere here, but still you are generating all these huge number of samples. So the proposal generation is highly inefficient because it's not informed by anything at all. You are just dividing the parameter space into equidistant points, and you are considering everything as a proposal in that range, right? And later on you end up rejecting all of them. Okay, so a proposal generation is highly inefficient. What if you have a way to generate proposals only in this particular region? So let's say you will generate proposals but only in this particular region. So what will happen is that even in this particular region there will be proposals with 0 posterior density and there are proposals with non-zero posterior density, but you will end up rejecting fewer samples. Okay, because if you generate proposal within this circle, then you are generating most of the proposals which would have some non-zero posterior density. So you are doing lesser wastage, right? So how do we do this, right? So this approach is called importance sampling. that rather than generating proposals based on grid points, basically dividing the parameter space into equal grid points. So, rather than doing that grid sampling, we will sample proposals from an importance density, okay, from a density which is closer to the posterior distribution. Okay. So, for example, if you know, let's say the or not know, let's say you have some idea that the posterior distribution of theta would be somewhat like this. So, it can range between, let's say, 0.6 and 1. Okay. So, in grid approximation, you sample proposals from uniform 0, 1. But what if, rather than sampling from uniform 0, 1, what if I sample theta star from, let's say, beta 2, 2. Okay. So, it is still covering all the values between 0 and 1. Okay. But what it is saying is that it will give you more values closer to 0.5 and fewer values from the boundary. Okay. So, boundary basically near 0 and 1, because those are not going to be very likely value of theta star. Okay. This could be slightly better in certain situations. Or let's say you generate proposals from theta star beta 2020. Okay. So, this is quite strict, but this can also work in certain situations. Okay. So, the point is to choose your proposals or to draw your proposals from a density which is closer to your posterior, or which is more likely to give you a large number of samples which would have non-zero posterior density. Okay. So, rather than drawing samples from clearly a uniform density between certain range, let's say A and B, you draw samples from a density q of theta. Okay. So, from this distribution q of theta, such that, let's say, if this is your true posterior p of theta given x, then q of theta is somewhat like this, that it is wider than the posterior, but it would be able to give you a lot of samples which are in non-zero posterior density and fewer samples from zero posterior density. So, basically you end up wasting fewer samples. Okay. But how do we do this? How do we choose a proposal density, and how do we implement this as a sampler from the posterior distribution, right? So, only change we need to make in grid approximation approach is in the proposal generation step. Remember 3 steps. Step 1 was generating proposals. So, proposal generation. So, this is the step that is going to change. So, rather than drawing samples from a uniform density or drawing the parameter space into equidistant points, we draw samples from a density called importance density from a proper distribution. Let's call it importance density. You can also call it proposal density. Okay. So, we draw samples from an importance density. So, the properties of this importance density should be like this. So, it has, let's say, fatter tails compared to your actual posterior. So, you need to basically decide based on what could be, where could your posterior lie, right? So, basically if you have some idea about the posterior, then you can better make this decision, or at least you can make this decision based on what values of theta are bound to have zero posterior density. So, what values of theta cannot be possible. Okay. Apart from that, you would allow all other values, right? So, it would have fatter tails compared to posterior, would be closer to the posterior, of course, right? So, these are the properties we desire in a good proposal density. If the proposal density does not have these properties, then it is also fine. It's just that it shouldn't be too off, completely off from the posterior. It shouldn't be a density that generates proposal which would never lie in high posterior density region, or it is never able to generate those proposals which are in high posterior density region, right? So, we do not want that. Okay. So for example, if this is your true posterior, then let's say your proposal density like this. So this is totally fine. If this is the true posterior and your proposal density is like this, then this is totally fine. So basically the proposal density will end up generating a lot of sample in high posterior density region. It would still generate samples which are in low posterior density region, but it is anyway better than, let's say, a uniform density that generates proposal, equidistant proposal between this point and this point. It is always more efficient than that one. Okay. So basically the goal is to make the proposal generation more efficient. Okay. So this is the only change you need. Of course, there will be one more change. So in step 2, you would evaluate proposals. You will weight these proposals based on their posterior densities. How do we do that? So unnormalized posterior density of theta star will given by likelihood of theta star, prior density of theta star. Okay. But now problem here is this, that theta star is already coming from a distribution which is q of theta star. Okay. So when you try to calculate this unnormalized posterior density of theta star, what is happening implicitly is this, that you are multiplying likelihood, because you are multiplying the likelihood here, you are also multiplying the prior density, and you are also multiplying this proposal density of theta star, because theta star are already coming from this proposal density. What does that mean? You will have lot of samples which are in high density regions of this proposal density and fewer samples which are in low density regions of this proposal density. Basically, this proposal density is likely to generate certain samples more than the others. So there is implicit distribution in all these samples theta star. So if you go on and calculate posterior distribution across these samples, and posterior distribution implicitly will have this bias of proposal density. Okay. So this won't give you, this thing won't give you the actual posterior distribution. This would give you a posterior distribution biased by proposal density, because all these samples that you are evaluating are coming from this proposal density. So basically what you are calculating here is this, likelihood into prior into proposal density. Okay. So basically this term is inducing this bias, right? In order to take out this bias, in order to take care of the fact that theta star is already coming from this proposal density, you can divide this thing by proposal density of theta star. Okay. Now you have basically taken care of that bias induced by this proposal density. So now when you calculate this unnormalized posterior density across all proposals, then the distribution you will get will be the actual posterior distribution. You are trying to estimate the actual posterior distribution, right? So this is how the weighting function will change now. So you will weight each proposal by this. So this is the unnormalized posterior density, likelihood into prior divided by its proposal density. Okay. And then step 3. Step 3 is accept or reject samples. For this you will follow the same approach, because this is giving you the weightings for each proposal. So you will get weights. Okay. So let's say this is theta 1, theta 2, theta 3. These are all proposals. Theta n, you are obtaining weights for each of them, right? So now you can do weighted sampling to get your posterior distribution. So this is the workflow of importance sampling, right? So what we have figured out, that grid approximation will become computationally inefficient, and this computational inefficiency will increase as the number of parameters will increase. So as you go from 1 to 2 parameters and you have this grid of a 2-dimensional grid, because the actual posterior would lie in a very small region of the grid. Okay. So this will become highly inefficient as the number of parameters will increase. Okay. So what is the solution? That can we improve this proposal generation step? This problem is happening because we are generating proposal all over the place. So this in this whole parameter space of mu and sigma, right? If we can limit the proposal generating space, then we can make it slightly more efficient, and that we do using importance sampling. So what happens in importance sampling is that you decide a proposal density q of theta, which is closer to the posterior, at least it covers the entire posterior, and you draw samples from that proposal density or importance density, and then you evaluate the proposals using this weighting function, and then you accept or reject the sample in the same way. So this approach will do slightly better, especially when you have two parameters, right? But there are still problems with this approach. And in fact, a more generic problem that will happen with both grid approximation and importance sampling, which is this, that how would you know that which range of parameter values are likely to have non-zero posterior density? Sometimes there is no way to know that, right? And if we make that sort of assumption based on data or something else, then that can lead to overfitting. So that can cause all sort of problems if you if you base this assumption on something else, right? So it's very difficult to decide that what kind of proposal density is a good proposal density. Okay, so how to choose the importance density? Okay, so it's not very straightforward. Also, it's very difficult to figure out what range of parameter values would have non-zero posterior density, right? So for example, it is very difficult to determine what parameter space I should divide as a grid in grid approximation. So for example, if you're talking about parameter mu of a normal likelihood, should I take values between 0 and 1000, or should I take values between 0 and 2000, or should I take values between 500 and 1000? Okay, these decisions are mostly arbitrary, right? So you may not have very good idea about this. Okay, this approach can totally work if you have very good experience of the same task. Let's say you are going to apply these methods on the same task again and again, then you might have very good idea and very good experience of what kind of values your posterior might have, right? In that case, this can work fine. But if you are in a completely new scenario, completely new likelihood, a complex likelihood which you have never worked with before, you might have very hard time in figuring out these importance densities and the grid points that you would want to create. Okay, so that's a big limitation of this approach. Also, even with importance sampling, okay, you will end up throwing away a lot of samples. You will still throw up all these samples in this region, right? So this is also not highly efficient sampling, right? So it's still a very poor. This is still a sampling with poor efficiency. Okay, the reason is this, that in order to generate these proposals, you are not using any information from your likelihood function and your prior density. Okay, you are just randomly relying on some intuition or some prior idea about this, or you are just randomly drawing samples from uniform density in case of grid approximation. You are not using any systematic information from your likelihood and prior densities, right? So that's why this approach is still inefficient, because your proposal generation step is something like you are drawing random samples from an independent density, which may or may not be efficient in terms of generating samples in the posterior density region, right? So if we can somehow use the information from the actual posterior distribution or the samples we have collected, so some information from our likelihood into prior density function, if you can use some information from this, then our proposal generation can become more efficient. So idea is this, that if this is the true posterior distribution, although you wouldn't know what is exactly the true posterior distribution, but you still have some idea about the shape of this posterior, in which points this posterior distribution would have higher posterior density region. You still have some idea. If you can use that information, if you can capitalize on that information to generate new proposals, so such that you generate a lot of proposals in this region, fewer proposals in this region and no proposal in this region, okay, then that can make our approach highly efficient, right? That we will figure out in next set of lectures, okay. For now, let us quickly try to implement importance sampling in R, okay. So let's see how to implement importance sampling in R for a simple example, okay. So we can actually so recently in one of the previous lectures we implemented we compared grid approximation against analytical approach. So let us now compare this also with importance sampling, right? So this was the example. So let's say you had an experiment where you are conducting 50 trials, and in each trial participant has to give correct incorrect response, and you repeat this experiment 5 times. So in experiment 1 the participant gives 45 correct responses, in 2 it gives 40 correct responses, in third it gives 39, and so on, right? So that's the experiment. So and you decide that the observed data points come from a binomial distribution where parameter theta has a beta distribution with A and B 90 and 10. So here we calculated analytical posterior. So analytical posterior would be a beta distribution with shape parameters A plus sum of observations, B plus sum of n minus observations. Okay, so this is how the analytical posterior looked like. Then we used the grid approximation approach. Okay, so in grid approximation approach we divided the parameter space between 0 and 1 into 10,000 equidistant grid points, and for each grid point we calculate likelihood, prior, unnormalized posterior density, which we use as weights in this sampling function to get 4,000 samples from our from this vector of theta, depending based on their weights as a normalized posterior density. Okay, so when we do this we get this posterior distribution using grid approximation, and we compared these two approaches here, right? So red one is samples from the analytical posterior density, blue one is from grid approximation, right? So let us also now draw samples using an importance sampling. Okay, so let us say, let me choose an importance density in this way. Let's say I will, so this is my importance density, beta density, beta distribution, and I'm going to generate 10,000 proposals from beta density with parameters, let's say 9 and 1. Let me just visualize how they would look like, okay, so that you know we are not deciding a very strict density. So I generated 10,000 proposals from this beta proposal density with shape parameters 9 and 1. And this is how it looks like. Basically, it is drawing a lot of samples close to 1, 0.9 and all this. It is still drawing a lot of samples in this region towards 0.4, 0.7, but is not drawing any samples beyond 0.4, okay, which is fine because this is a response accuracy experiment and you do not expect people to have accuracy of less than 0.4. Okay, so this is fine. So now for each of these theta we will do the same things. We will calculate likelihood, prior, but now unnormalized posterior density should be basically this bias we need to take off. So basically we will divide this thing by proposal density of theta star. Okay, so proposal density of theta, so basically d beta theta 9 1. This is proposal density, or maybe I can write it here. Proposal density will be this. Okay, so when I calculate unnormalized posterior density, I divide this thing by proposal density. So this will, now I can draw samples based on importance sampling, calling it IS. Okay, so these are the samples based on importance density. Okay, now I can compare samples from all three approaches. So I'm just adding to the same data frame samples from the importance sampling method. So here I can write repeat importance sampling 4000 times. Okay. Yes. So now it gives me estimation using these three methods. So the red one is analytical posterior density, the green one is grid approximation method, and the blue one is importance sampling, right? And they look similar. For example, at least the range looks similar because it was a very simple case with one parameter and very simple binomial likelihood, right? So that's why you wouldn't see a huge difference between these three approaches. But as we go through more complex cases of likelihood and more complex prior distribution and all, then you will clearly see some differences across these three approaches. What you should see, that importance sampling should be better than grid approximation. Okay. So that you can even see here. So what if the if let's say the data point is such that it is strictly like this 44, 43, right, and the prior is, let's say, 8 and 2, right? Now you might see more difference between the three approaches. Yes, red one is analytical, blue one is approximation using importance sampling, and see the green one now, it has too many peaks, so you get a very weird posterior recovery using grid approximation. Okay, so red one and blue one, so red one is of course it's analytically derived, so blue one has good posterior recovery, okay, compared to it's a green one. Okay, you will see this difference more clear as you go towards more complex models. Okay, we can see few of such examples in later lectures. Okay, so I will stop here for this lecture on importance sampling. Okay, so you can give it a try. You can try it yourself at home using simple examples that how to implement importance sampling. Everything is same except the proposal generation step. Okay, so here we have completed these two very simple computational methods of estimating the posterior distribution. Okay, next lecture onwards we will start much more sophisticated methods of estimating the posterior distribution, which would be basically Markov chain Monte Carlo and Hamiltonian Monte Carlo. Okay, and those methods would have a very important advantage over existing methods, that is they will do dependent sampling. So they will use some information from the samples that you have already collected to propose further samples and to accept or reject further samples, right? So we will see how do we do that. Okay, so I will stop here. In the next lecture we will discuss Markov chain Monte Carlo. All right, thank you.